If there's one thing you've learned taking a chemistry class, it's that chemists love moles. We love to measure how many atoms or molecules we have with this really big number. Remember, it's 6.02 times 10 to the 23rd. That's 6 with 23 zeros behind it. And we use it to count atoms and molecules. But have you ever wondered just how big is a mole? How much space does it take up? That's just what we'll look at in this lesson. We'll actually look at how large a mole of gas molecules will be. And this is actually an interesting application of the ideal gas law. We'll specify the temperature, say room temperature, and the pressure, maybe atmospheric pressure, the pressure all around us all the time. And once we plug in those pressures and temperatures, then we can figure out how much space a mole will always take up. Let's figure out just how big a mole of gas is. In this lesson, we'll derive molar volume with the ideal gas law, we'll compare the molar volume of different gases, and use molar volume to solve some problems. But first, what is this molar volume thing? We'll begin to think about that by looking at a tablespoon of water. Now, this is liquid, but in a tablespoon, there's approximately 6.02 times 10 to the 23rd molecules of water. Okay, that is exactly what we mean by molar volume. It's the volume occupied by exactly 1 mole, because 6.02 times 10 to the 23rd molecules is a mole, about a trillion molecules. So there's tons and tons of molecules in a tablespoon of liquid. But the amount of space that a mole takes up depends on its phase. How could we figure it out for a gas? That's where the ideal gas law comes in. We can solve for the molar volume of a gas. How can we do that? Well, recall that we want to know the volume of exactly 1 mole. So what are we going to plug in here? Into our moles, exactly 1. So we're going to plug 1 mole in for N, and then we're going to calculate our volume. Of course, as you would realize looking at this equation, we'll also have to plug in a temperature and a pressure. And what that means is the volume of a mole of gas depends on temperature and pressure. So we're going to calculate the molar volume of a gas at just one particular temperature and pressure. What temperature and pressure should we choose? We're going to choose the standard temperature and pressure. So this question says, find the molar volume of gas at standard temperature and pressure. What's standard temperature and pressure? Well, it is 1 atm and 0 degrees Celsius. So if you ever see STP floating around in your gas law problems, that's telling you the temperature and pressure. The pressure being 1 atm and the temperature being 0 degrees Celsius. Okay, well let's use this pressure and temperature to calculate the volume of 1 mole. Here's our ideal gas law and our Celsius to Kelvin conversion. Let's start by writing down the variables we know. We know the pressure is 1 atm. We know that the temperature is 0 degrees Celsius. And then we know moles. How many moles do we have? Well, because we're looking for molar volume, again, we're going to want to plug in exactly 1 mole. And what we're looking for is volume. How much space will that 1 mole take up? Okay, now if I think about the pressure, I know that my units are in atm, which is what I want them to be in. But my temperature is in Celsius, and that is not where I want it to be. I want it to be in Kelvin. So we're going to go ahead and convert that to Kelvin by adding 273. And we'll get 273 Kelvin, which is the standard temperature in Kelvin. Now let's solve for volume. We'll plug in our pressure, which is 1, and we'll multiply that by volume, which is our unknown, so that's V. So we plugged in P and V, and that's going to be equal to our moles, which again is 1, times our gas constant, which recall is 0.0821, times temperature, and our temperature is 273 Kelvin. Now we need to get volume by itself, but because it's multiplied by 1, it actually already is by itself. So volume is equal to 1 times 0.0821 times 273. If I do that, I'm going to get 22.4 liters. What does that mean? That means that 1 mole of gas is equal to 22.4 liters. So if I ever have 1 mole of gas, I know that its volume is 22.4 liters. Of course, that's only at one very specific temperature and pressure. This is at STP. This allows us to solve lots of problems, easily going back and forth between moles and liters. Well, how big is that 22.4 liters? It's about the size of a beach ball. So a beach ball contains about a mole of gas. Now, realize that's way bigger than a tablespoon of liquid water. but they contain the same amount of molecules. What that tells you is gases are really spread out compared to liquids, which we hopefully already knew. Okay, now the thing is that even though molar volume is about 22.4 liters, it turns out to vary some. So molar volume varies depending on the gas. If we look at ammonia, NH3, we get exactly 22.4 liters. So that one behaves exactly like we expect. But argon, notice, is 22.09 liters, not quite the same. It turns out that when we use the ideal gas law, we're making certain assumptions about how gases behave. We won't go into the details of those assumptions, but just realize that the number we get out from the ideal gas law is just approximate. It's a really good estimate. And that's why you'll see that this molar volume varies. CO2, for example, is right back at 22.40. Chlorine is a little small at 22.06, and things like hydrogen are a little big. So molar volume does vary, but it's all really close to 22.4. Okay, let's solve some problems with molar volume. This asks us to use molar volume of an ideal gas to solve each of the problems below, and it tells us 22.4 liters equals 1 mole at STP. All right, go ahead and pause the lesson and see if you can use that conversion factor to solve some of these problems. Well, for A, we're given liters, and we're asked for moles. So we're going to start by writing down 415 liters. And we know we want to go to moles. And so what that means is we're going to put liters on the bottom and moles up top. Liters will cancel out, giving us moles. What numbers do I plug in? Well, 22.4 goes with liters, and 1 goes with moles. When I do that and round to 3 sig figs, I'll get 18.5. So that's how many moles there are in 415 liters. So what looked like an ideal gas law problem that might have taken a long time, we can do really quickly. The next problem asks us to go the opposite direction from 0.500 moles of oxygen to liters. And so we want to go moles to liters. This is just the opposite direction, which means we'll flip our conversion factor. Here what we'll do is we'll put our moles on the bottom and our liters up top. So we get 22.4 liters is equal to 1 mole. When I multiply that 0.5 by 22.4, I get 11.2 liters of oxygen. So again, we went really quickly between liters and moles. This next problem will involve 2 steps. It asks us to go from liters to grams. So remember that moles and grams are like 2 sides of the same coin. So we'll start with liters, go to moles, and then we'll figure out how to go to grams. Okay, to go from liters to moles, we know how to do that already. We put 22.4 liters on the bottom and 1 mole up top. Now comes the new step, which isn't really a new step. We've done it over and over again, is we're going to go ahead and go to grams using our molar mass. So we want to have mole on the bottom to get rid of our moles, and we want to have grams up top to go to grams. And we're told that the molar mass of nitrogen is 28.02, so that means 28.02 goes up top and 1 goes on the bottom. So when I take 114, divide by 22.4, and multiply by 28.02, I'll get that this is equal to 143 grams of our nitrogen. In this lesson, we've derived molar volume with the ideal gas law, we've compared the molar volumes of different gases, and we've used molar volume to solve problems. Hey, hey.